Early in the week, we discussed the Shockley-Queisser limit as a fundamental limit for conversion efficiency of a single-junction solar cell. A key word here is single junction. In this video, we will introduce the concept of multi-junction solar cells. They are used to surpass the theoretical maximum conversion efficiency of single-junction solar cells, the so-called Shockley-Queisser limit. This diagram shows the design rules for increasing the efficiency of solar cells. Beta spectral utilization is achieved by the choice of absorber materials that build a solar cell. As discussed before, the number of photons that are absorbed by a solar cell and consequently the photocurrent are constrained by the bandgap of the absorber material. The quality of materials and interfaces determine the bandgap utilization of absorbers and the fill factor. As we learned from the previous video, the open circuit voltage is directly related to the bandgap utilization. The recombination processes in the bulk of materials and at their interfaces decrease the amount of photogenerated charge carriers. Defects and contacts that result in series and shunt resistances also lower performance of solar cells. Therefore, defect elimination is one of the most important areas in solar cell engineering. Light management aims to reduce the optical losses in solar cells. In this area, the focus is on optimal design of rough interfaces for efficient scattering and diffraction of light, low absorbing and high conductive transparent electrodes, and design of anti-reflection structures and coatings. These three design rules affect each other, and thus the overall improvement of the solar cell efficiency is a delicate interplay among them. In this video, we will focus on the multi-junction concept to increase the spectral utilization. Single-junction solar cells can only utilize a fraction of the energy of incident light. This figure illustrates the spectral utilization of the AM1.5 spectrum by a single-junction crystalline silicon solar cell. The spectral irradiance of the AM1.5 spectrum is represented by the yellow area. The brown area shows the fraction of the spectrum which energy can be converted into electricity by a single-junction crystalline silicon solar cell. Crystalline silicon absorber has a bandgap energy of 1.12 electron volts, which corresponds to a wavelength of roughly 1110 nanometers. Much of the energy in the short wavelengths region is lost due to thermal relaxation. Part of the spectrum, the long wavelength region, is not utilized due to the non-absorption. The fraction of AM1.5 spectrum that can be converted by a solar cell into electricity is defined as the ultimate conversion efficiency. This efficiency of the solar cell does not take the additional optical and collection losses into account. As we have learned earlier in this week, the ultimate conversion efficiency is calculated with this equation. The bandgap of the material is taken into account because solar cells can efficiently use only photons that have a smaller wavelength than the wavelength corresponding to the bandgap of the absorber. The maximal ultimate conversion efficiency of AM1.5 spectrum is 48%. This performance can be achieved with a single-junction solar cell having an absorber bandgap of 1.2 electron volts. When the Shockley-Queisser approach is applied and the bandgap utilization efficiency and fill factor are taken into account, the efficiency drops to around 33%. To utilize a larger part of the solar spectrum and thus to boost the conversion efficiency of solar cells, a so-called tandem or multi-junction solar cell concept is developed and applied. This means that we fabricate solar cells that are based on a stack of 2 or more solar cells that we call component solar cells. These tandem solar cells have multiple p-n junctions that are used and they use semiconductor materials of different band gap. As a result, photons from a larger part of solar spectrum can be absorbed. Using this approach, non-absorption and thermalization losses can be strongly reduced. Now, let's look at the spectral utilization of a double-junction solar cell. This double-junction solar cell is composed of a top and bottom cell, the top cell with wide bandgap absorber and the bottom cell with low bandgap absorber. The blue area represents the fraction of energy that can be used by the top cell. The bandgap of absorber here is 1.7 electron volts, which corresponds to a wavelength of around 700 nanometers. The portion of energy that can be used by the bottom cell is marked in brown. The bottom cell absorber has a bandgap of about 1.2 electron volts, corresponding to a wavelength of around 1100 nanometers. Incident light first passes through a high bandgap absorber material. This layer only absorbs high energy photons. Lower energy photons are not absorbed in this layer because this layer is transparent for them. The low energy photons are absorbed by the second absorber layer with a lower bandgap. By stacking together 2 solar cells with absorber layers of different bandgap, we reduce the thermalization loss and the non-absorption. In this case, as you can see, the ultimate conversion efficiency increases to 65%. When applying Shockley-Quasar limit, this double-junction solar cell can achieve a maximal conversion efficiency of 45%. We can stack one more solar cell to make a triple-junction solar cell. The blue area represents the fraction of spectrum utilized by the top cell. The brown area represents the fraction absorbed by the middle cell, while the pink area is the fraction absorbed by the bottom cell. By tuning the bandgap of the absorber layers in a triple junction cell, we raise the ultimate conversion efficiency above 70% and the theoretical achievable conversion efficiency to 51%. The concept of multi-junction solar cell aims at reducing the thermalization loss and non-absorption loss. As you can see on the left, when we only have a single junction solar cell, a large amount of photon energy is lost through thermalization. When we stack absorber layers with different bandgap together, excess energy lost through thermalization is reduced. Despite the advantage of spectral utilization enhancement by multi-junction solar cells, there is one major issue which needs to be addressed to really have a high-efficiency multi-junction cell. Here you see a schematic figure of a triple-junction solar cell. The blue block represents the top cell with a wide bandgap absorber. You can see from the JV curve on the right that the individual top solar cell has usually a high open circuit voltage and a low short circuit current. The red block represents the bottom component cell. In contrast to the top cell, the bottom cell has an absorber with a low bandgap. This solar cell has usually a low open circuit voltage and a high short circuit current. The middle cell is represented in green, and it has an absorber with a bandgap between top and bottom cell absorber. When we stack these 3 solar cells on top of each other in a 2-terminal device, the component cells are connected in series. In other words, the individual cells in triple junction solar cell are electrically and mechanically coupled together. When component cells are connected in series, the resulting voltage is the sum of voltages of individual cells. However, the current density of the triple junction cell is limited by the component cell that generate the lowest current density. This current mismatch is demonstrated by the gray JV curve of the triple junction solar cell. The resulting open circuit voltage is the sum of open circuit voltages of individual cells, while the short circuit current density is limited by the lowest current density delivered by the top cell. To achieve current matching between the individual cells in a triple junction solar cell, the absorber thickness of each component cell must be optimized. We see from the diagram of JV curve that in the optimal situation, the maximum power point each component cells delivers the same current density. You can calculate the optimum absorber thicknesses for current matching if you know the refractive index and the absorption coefficient of all the materials in a solar cell. For this, you will need the Fresnel equations and an understanding of how light is absorbed in a solar cell. You learned these concepts earlier in this course. You can avoid current matching if you use different configurations of a tandem solar cell. First, it is a tandem solar cell which has two terminals. The tandem cell with two terminals has individual cells electrically and mechanically coupled together. In this configuration, current from individual cells must be matched at their maximum power point to avoid power losses. To circumvent the current matching issue, a tandem cell can be fabricated with four terminals, so that individual cells, while mechanically coupled, are electrically decoupled. By removing the constraints of current matching, we no longer need to control the absorber thickness and parasitic absorption in the supporting layers of each component cell precisely. We can further decouple individual cells mechanically so that we have more freedom in fabrication of tandem cells. As you can imagine, these last two configurations are more complicated to use when connecting a solar cell to an external circuit. Therefore, in practice, we rarely use anything aside from the two-terminal device. This means that we almost always have to consider current matching when designing multi-junction solar cells. In summary, in order to increase energy utilization of solar spectrum, multiple junction solar cells with absorbers of different bandgap can be fabricated. In these multi-junction solar cells, the amount of lost excess energy of absorbed photons can be decreased. Finally, you learn that current matching is of great importance when designing multi-junction solar cells. There are some ways to get around current matching, but in practice, they are rarely used for real solar cell applications. Another final note is that multi-junction solar cells also have some drawbacks. Adding junctions adds complexity to the cell and to the fabrication process. This will increase costs to the production. However, there are still cases where it is worth it to use the multi-junction concept, and you can learn about this in the photovoltaic technologies course.